Okay, our third video, final video here for the second section of chapter 3. We're going to conclude here with some problems on finding domain. So let's talk a little bit about, before we do that, the basic definition of a logarithm. We said that the log base a of x is equal to y. What this means is that a to the y power is going to produce x. Well, what kinds of things can this possibly be then? Or what can't it be? Well, if I take a number to a power, what am I not going to get? And the answer to that is I'm not going to get negative answers. I'm going to get something greater than 0, for that matter. And I'm not even going to get 0. So, and I believe I included this back in the basic, in the first slide. Let me double check that. I did. All right, I said that the x value here, this has to be greater than 0. So we keep that in mind. This cannot be 0, it cannot be negative. So as far as finding our domain then, let's get back down to that slide. It's my last one, here it is. As far as finding the domain, that means that I have to say, well, in this case, this must be greater than 0. So that gives me a simple linear inequality to solve. So I'm going to say, well, x plus 3 must be greater than 0. So when I solve this, x must be greater than negative 3. So that's my domain. My domain is all values that are greater than negative 3. Pause the video and try the others here. This one here, 3x minus 1, also has to be greater than 0. So this gives me 3x is going to be greater than 1 when I add the 1, so x is going to have to be greater than 1/3. Just beware, if you ever divide or multiply both sides by a negative, you'll have to change this sign. Don't forget that little rule. If I had thought about it, I would have put one in here that you have to do that, but this will do. So here we have 5x plus 10. Now the same thing works for natural logs. Okay, 5x plus 10, this has to be a positive value. So 5x is going to be greater than negative 10. If I divide by 5, x has to be greater than negative 2. So all x values greater than negative 2 will be in the domain for that function. And this one here, x squared has to be greater than 0. So what that means is that x has to be greater than 0. I take that back. I just messed up there. When I square a negative number, I'm going to get a number greater than 0 too. So here, x can equal anything except for one value. X cannot equal 0. Anything other than that, you'll be okay. But if x is 0, 0 squared equals 0, it will not give you something greater than 0. But say if x is negative 2 squared, if you do it right, negative 2 times negative 2 is positive 4. That takes care of that. So that takes care of that. Now, one thing I just realized I did not mention, but I think we've seen enough of these by now that you'll probably have very little problem with the transition. Regarding the graphs, the shifting rules, the transformation rules, are going to apply. So if I have a function that I'm graphing, say for instance, I'm trying to graph f of x equals log of, say, x minus 6. Well, this is the same thing as a horizontal shift. We've seen that several times before. So this is going to be the graph of just regular old log of x, except it's going to be moved. And this number here tells me where it's going to move. Where would it go? It would go right 6 places. So I can demonstrate that here to you real quick. If I compare, I think I still have log of x in there. Yep. So there's regular log of x. Now if I look at the log of x minus 6 in a parentheses, let me move the window right here a little bit so we can see it a little better. There it is. So it's been moved 6 places to the right. Now again, we're not seeing the asymptote. Our calculator is limited with regards to what it can display, but what I wanted to show you here is that the graph got shifted 6 places to the right. So we think about what about vertical shift? What about just lowering the graph? Well, what if we considered a graph of the function log of x, and then not inside of the parentheses, we put a minus 6 outside here like that. This should lower the graph 6 places. So let's see if that is what happens. So we'll replace the second graph here with the log of x. I'll close the parentheses and I'll subtract 6 from the entire thing. So we should see it's lowered 6 places. Other than that, it's the same exact graph. The only way we're going to change the graph is if we multiply by something. And so all the same rules apply with regards to shifting graphs. And I put a few problems on the homework pertaining to that. You will see it on the test, and so I think it's only fair that you see that in your homework. So what we'll do here, this is a lot of information here, and it's something that I really want to make sure that you get. So on page 195, we'll see a problem set that begins, and we're going to do, I planned on 1 through 43 odd. Some of these are really quick. They're not all graphing or anything like that, but I know it's a lot of work, but you really have to make sure that you understand this. In addition to that, I'm giving you 45 through 52. There's 4 matching problems in that. Match the equation to the graph, just based on the shifting that I just mentioned to you right now. And in addition to that, we've got some problems that are asking that you describe one graph from another one. For example, what I just showed you. If I tell you that f of x is the log of x, and then I make up another function called g of x, which is log of x plus 2, written like that, you have to tell me, what am I going to do to, how is this graph going to be changed into that one? So this graph, you would say, would be shifted 2 places up. Yeah, so we could just say shifted up 2 units. And that'd be good enough. As for the rest of them, a lot of problems involving evaluation. So evaluate certain logarithmic functions or expressions at particular values. Important, to get the repetition and to make sure that you understand this. That's it.